Alright, this is the notes for section 8.4, areas of triangles. If you haven't done so already, make sure that you complete the reading for section 8.4 before you continue on with these notes. To begin with, I'm going to go back to the idea that all of our formulas really are derived from the rectangle formula. And we're going to start by looking at finding an equation or a formula for the area of a right triangle. Well, we already have established that if I look at a rectangle, we can take its length times its width, or its base times its height, whatever you want to call it. But I'm gonna multiply those two things together to get the area inside. Okay, that was one of our postulates. Now, if I take that rectangle and if I draw in one of its diagonals, what it does is it splits that rectangle into two congruent triangles. And since they're congruent triangles, we know that those congruent triangles have to have the same area. Therefore, the area of a right triangle must be exactly half of the area of the rectangle. So that's how we're coming up with our formula for the area of a right triangle. And the area of a right triangle then is the area is equal to 1/2 the base times the height, where we say the base and the height are the legs of that right triangle. So let's take a look at example 1 here, where we're going to apply that area formula for this particular right triangle. It says find the area of a right triangle with lengths of 8, 15, and 17. Well, we know that 17 is the hypotenuse of that right triangle. Therefore, 8 and 15 have to be the legs of it. And it really doesn't matter how you label that, as long as you know that 8 and 15 represent the length of the legs of that right triangle. So what I'm going to do is I'm going to write down the formula. Area is equal to 1/2 BH. Therefore, area is equal to 1/2 times 8 times 15. If I go ahead and multiply that out, then 1/2 times 8 is 4, and 4 times 15 is 60. Therefore, the area of that would be 60, and remember, it's square units. Alright, a term as we work with triangles that we need to be familiar with is the term altitude. And altitude and height are usually used interchangeably, but when we refer to an altitude of a triangle, we're talking about a perpendicular segment. So something that we can draw in, a perpendicular segment, and it goes from a vertex to the line containing the opposite side. Okay? So basically what that means is that we can always take that opposite side and we can extend that segment out and make a line out of it, because sometimes the altitude is going to lie outside of the triangle. Okay, an altitude can lie inside, outside, or be an actual side of the triangle. So let's with that in mind, let's kind of take a look at that next example then. Okay, so let's take a look at example 2 here. It says draw the altitude for each of the triangles, and we have 3 different shaped triangles here, but I want to draw an altitude for each of them. Remember, each of them actually has 3 altitudes, but let's just draw one in for each of them. So if I look at this first one, if I were to draw in an altitude for the first one, if I pick this to be the vertex point that I want to work from right here, so if this is the vertex point that I'm going to work from, I'm going to draw a segment going from that vertex point perpendicular to the side right down here. So since that is going to be inside the triangle, we don't have to worry about extending the line at all. So I can draw in that line segment, and we'll do that here. So it's going to be something like that for the altitude. Okay, going from the vertex point perpendicular to the side opposite it. So this would represent the altitude of that triangle. Okay. On the second one over here, what I need to do is I need to, if I'm going to go from this vertex point up here, okay, if I'm going to go from that vertex point, I'm going to need to extend this side, the opposite side, out, because my altitude is actually going to be outside of the triangle. So I'm going to draw that in now. So the red segment that I've drawn in here would represent the altitude from this vertex point at the top of the triangle. Now remember, every triangle has three altitudes. One from each of the different vertices. Now to do that, you'll notice that I extended this line. I just made it a dotted line. So I'm just extending the line of the opposite side, so that I can drop my altitude down to the line containing that opposite side. Okay, finally this last one then. This last one is a right triangle already. And if it's a right triangle, then I can say that each of these base sides, or each of the legs of that right triangle, are actually altitudes of the right triangle as well. So that's where we've got an example where it lies inside, one where it lies outside, and finally one where it's a side of the triangle. So we've established the formula for finding the area of a right triangle. We can actually apply that exact same formula as we look at the area of any triangle. Now in the book they went through a proof of this. I'm not going to go into detail about that. You can get that from your reading, but I do want you to be familiar with what the area formula is. And when I say B and I say H, B represents a base, and any side of a triangle can be the base, as long as H, the altitude or the height or the length of the altitude, as long as that is measured to that base. So if this is the base, the altitude has to be measured to the vertex opposite that. So this would be a good picture of what base and height would represent. So we can now use that formula to find the area of any triangle. So let's take a look at example 3 here. It says, using the figure at right, find the area of each triangle. Well, to find the area of each of those triangles, I need two numbers for each of them, and that's one is I need to know what the length of the base is, and the other thing that I need to know is what is the height, or what is the length of the altitude. Well, if you think about P as being the vertex point, P is a vertex point in all of the triangles that are there. And if you look at that, then RP could represent the altitude of every one of those triangles. And I know that RP, that length, is equal to the distance from, in terms of, we're talking about a distance that's going horizontally, but that's okay, going from 0 to 6. Therefore, the length of RP is 6 units. Okay. Now, that represents the height in every one of those triangles. And then to find the area, all I need to know is the base for those. So I'm going to do part A, and then I'm going to leave B, C, and D for you to do. So part A, if I'm going to find the area of that triangle, I'm looking at PQS. PQS, that would be the triangle that has a base right here. Okay. Well, that base goes vertically from 0 up to 6. So that would, I take that back, up to 5, sorry. Therefore, if I'm going to find the area of that, I'm going to take 1/2 times the base, which is 5, times the height, which is 6. Or 1/2 times 30, or 15 square units. Okay. So the other problems there, B, C, and D, I'm going to leave for you to do, and then we can talk about those in class. So let's take a look at example 3 now. It says find the area of the triangle ABC with A equal to 0, 3, B 6, 3, and C 4, 8. So the first thing I'm going to do before I find that area is I'm actually going to graph that triangle on the grid below, and I'd like you to do the same with me here. Okay, so I've plotted those points, and I have my triangle drawn here. So what I want to do now is I want to find the area of it. Well, to do that, once again, I need two pieces of information. What is the base and what is the height? Well, it works out very nicely if I work with this base that is a horizontal base. So I'm going to do that. My horizontal base goes from 0 all the way over to 6. Therefore, that would be 6 units. And if I go with a height going from here up to here, there's my altitude that I've drawn in. It's perpendicular to the base, and that is 5 units up. Therefore, the area of that triangle is going to be equal to 1/2 the base times the height. Therefore, the area is going to be equal to 1/2 times 6 times 5. And it actually turns out that that area is exactly the same as the one that I started out with in number 2, and that is 15 square units. Alright, the last problem I'd like to take a look at is example number 2 here. It says, or excuse me, example 4. It says if the area of triangle LON is 150 square units, find IN. Okay, so now what I'm doing is I'm using my formula to find something other than area if I know area. So area is equal to 1/2 the base times the height. So what I want to do is I'm going to plug into my formula the things that I know. I know the area, so I'm going to plug that in for A. 1/2 stays the same. I know that the base of this triangle, if I have 8 units from L to I and 12 units from I to O, if I add those two together, that will give me the base of that triangle, which would have to be 20 units. Okay? The only thing I don't know is the length of my altitude, IN. Okay, and that's what I'm looking for. I'm just going to leave that as H for right now. So now I'm just going to solve this equation for H. So I have 150 is equal to 10H, and if I divide by 10 on both sides, H would be equal to 15. Therefore, the height of this figure would be 15 units.